Okay, welcome to the course. Let me first make a small summary of what we're going to see today. Today we're going to keep talking about graph theory. So how graphs let us understand social networks. We'll start by continuing. We have one more example from last week where we have, remember we had strong weak links plus local bridges. So we're going to generalize this. And then we're going to talk about similarity. People on networks who are friends of each other usually have something in common. So that's what we will talk about. We'll talk about social affiliation networks. Okay, so a social network is just a graph when you have a link when people are friends. But we want to know why they are friends. So we put something extra in the network. It's called affiliation. Then we have three kinds of closure instead of just one. Remember last week I mentioned Triadic Closure. It's a very sophisticated name. It's a word to say that if you have two friends in common, probably they will also become friends. So the friends of friends become friends. So in order to not use too much the word friends, this is called triadic closure. Okay? But if you have social affiliation networks, this will tell us why they are friends in the network. And then actually, instead of just one kind of closure, we have three kinds of closure. And then I'll make some empirical studies. So this is studied for the internet. And also we have a really nice Wikipedia study that I'm going to explain. And the final thing is positive and negative relationships. So friends and enemies. So you see we get more and more powerful. Up to here, it's only friends. They may be close friends or just acquaintances, but it's all positive, okay? But now in this final part we'll talk also about enemies, okay? What happens when two people or two countries are enemies? And that gives us also really interesting insight. So that's something we'll see also. Okay? So all of this is part of graph theory. Remember, later on we'll also see game theory and market economics, okay, in this course. But right now we're still in graph theory, and this is already telling us many things, okay? So the first thing I want to do, this is what we saw last week, was Granovetter. The funny thing is that Granovetter found that if A and B, they're connected by local bridge. It means that they don't have any friends in common. If you remove that link, it separates everything, okay? And that means A has extra information, but the link there in between is going to be weak, okay? So there's a connection between strong, weak, the strength of the link, and whether it's a local bridges or not bridge, or not a bridge. Whether you separate the graph, so it's only one connection as a local bridge, so that's it. Whether the connection is kind of fragile, and whether the link is strong or weak, okay? So we saw that last time, but here we only have two things, strong, weak. It's like binary. And here it's a local bridge or it's not. It's binary, okay? Now we're going to turn these into numbers, generalized measures, okay? So the idea is we're going to keep talking about tie strength and local bridges. So how the nodes are friends or not. So how strong it is, strong or weak here. That's tie strength. And then the weak, the local bridge is whether there's a separation here. Whether these two parts of the network are really separate. That means there's no other friends in common. So this is whether it's a bridge, and this other thing is whether it's strong or weak. So there's two separate properties, okay? This bridge is a structural property. This is mathematical, the bridge, okay? And the strong weak is sociology. So again, we are connecting mathematics, graph theory, and psychology of people, okay? So it's not, this course is not pure mathematics, it's connecting mathematics to people, okay? But this is too naive somehow. Strong or weak, there's only two ways, either your friend or acquaintance. And the bridge, it's either bridge or not. But in realistic networks, we want to be more flexible. We have some numerical number, how strong it is, going from 0 to 1, for example. Or here, instead of local bridges, it says how local is the bridge. It's really local bridge, or maybe it's almost a local bridge. So we need some kind of number. Okay, so for both of these, we're going to use numbers. And then I'll show you, then people actually measure it for real things, Facebook and Twitter, and how what you see, okay? So the first thing I want to do is generalize local bridges. And this is called, the number I come up with is called neighborhood overlap. So this number goes from 0 to 1, and if it's exactly 0, then we have a local bridge. But if it's almost 0, close to 0, then it's like almost a local bridge. And the farther it goes away from 0, the less the bridge is local bridge, okay? So this is defined in terms of the graph. We take the number of nodes who are neighbors of both A and B. So this is for nodes A and B, for nodes that are neighbors of both, divided by the number of nodes who were neighbors of at least one. Now, if you actually work this out, if I have a local bridge, remember we have a local bridge, we have A and B, and then maybe some other very long path here. So this is a local bridge. But A and B have no nodes that are neighbors of both A and B. So C could be a friend of A and a friend of B, but there's none of them, 0. Okay? So this would give 0 for the top. And the number of nodes who were neighbors of at least one of A and B, that's very many. That's all these, it's all these, so there's very many of those. So we get 0 divided by some big number. Okay, so for a local bridge, that number is 0. You see it, Okay? Now, if it's almost a local bridge, let's say there's one node here who's friend of both A and B. Okay, it's almost. And then we would have 1 divided by some big number. So it's still almost 0, okay? But if there's a lot of nodes in common, if there's very many, or maybe A and B are really connected, then this number gets very big. And if all of the nodes are in common, if A and B are like this, so all of their friends are in common, then it's like exactly the opposite of a local bridge. The number is equal to 1. Okay? So we go from local bridge to neighborhood overlap. So basically, the intuition is, every node has a neighborhood, which is all the friends. And the idea is if the neighborhood of A and B are really overlapping, then it's not a local bridge. Okay? So neighborhood overlap is a good intuition for C. You see it's 0 for local bridge, huh? So this is neighborhood overlap. Overlap, okay? So this number goes from 0 to 1, whereas local bridges, it's binary, yeah? Yes, no. Here it goes from 0 to 1. Here you have local bridge at 0, and here you have no local bridge, okay? And in between, it's like a little bit local bridge, okay? And tie strength is an easier number, okay? Instead of strong, weak, we will have the strength going from 0 to 1, okay? So we kind of define it arbitrarily. Like if two people in a Facebook are sending messages to each other, the more messages they send, the higher the number. So we maybe divide it by some maximum, and then we get some kind of a numerical value. Huh? So for strength, too. And then we get something like this. So this is some social network. So this is some network in some article. Here you have the strength. So here you have very close friends. And on the left you have, they almost don't know each other. Okay? And on the vertical you have the neighborhood overlap. So the lower it gets, the more it's closer to a local bridge. Huh? Here it's like local bridge, 0, and up there it's like the opposite. They have a lot of friends in common. Okay? So according to Granovetter, this is what we saw last week. Okay? Granovetter said that local bridges have to be weak, because if they were strong, you would have triadic closure. Okay? But this graph shows actually the same thing. So a local bridge, which is here, the lower number, is weak. So you see, the function is going up. So it's like saying the same thing as Granovetter, but now with numbers. We have some range of numbers, okay? So as we get closer to local bridge, the tie gets weaker, okay? So as the neighborhood overlap goes to 0, the tie gets weaker. So this is kind of saying the same thing as Granovetter, right? And strong ties have more neighborhood overlap. That's reasonable from triadic closure. Huh? If you have two friends and they're very close friends, probably they will become friends. Okay, so strong ties have more overlap. Here's another example. So in this course I'm going to show lots of examples of like real software. Huh? So this is coming from Facebook. So at Facebook, how do we define the strength? Well, there's different ways people can talk to each other. So I assume that most people know Facebook, so I'm not going to explain so much how it works. Okay? So you have friends on Facebook, and the strongest is if the two friends are actually sending messages to each other, back and forth. So that's pretty strong. They are individual, they know each other. Okay, weak, a little bit weaker is if it's one way. Okay, if I send messages to somebody but no reply, they're listening to me but they're not replying, that's weaker. They're not really close friends. Also, I'm following somebody, but I'm not actually sending them anything. Okay? So Facebook, of course, makes a lot of money out of that. They say, look, we have so many friends, but most of those friends are not really very close. You know that, So the weaker one is you follow somebody. So sometimes you look at their page, whatever, but you don't actually communicate with them. And the really weakest is you declare someone as friend, but nobody is looking at the guy, okay? It's just declared. I have declared 10 million friends. But nobody is looking at my homepage. There's still 10 million friends, right? But that's very weak. So you can see, you can make also the strength there in Facebook. You can define stronger or weaker. And here's different graphs. This is a part of a big Facebook. So this is like a local part of this huge Facebook graph. And you can see this, so these are the 4 strengths, okay? You can see this one, this is where they're actually talking back and forth. Very strong friends. You see there's not so many, It's very, very light here. There's not so many very strong friends. It's normal, But one way, it's a little bit more, okay? And then the maintained relationships, where sometimes I look at somebody's page, but I don't communicate. It's even more. But then the ones that are just declared, but nothing happens, there's even a lot more, okay? So Facebook says to the advertisers, look at that. Please, you have to pay a lot to make ads, okay? But what's really happening is only this, okay? In fact, mostly, So that's the way the world works, So you see how Facebook friends, the stronger they are, the less there are. And you can make a graph of that. Okay, so here the solid line is the mutual communication. Here it's called reciprocal. So this is where they talk to each other. So you see there's not so many. As the network goes bigger, you have a little bit more, but there's not so many. Whereas the weak ones, this is the ones where you sometimes look at the page, but no communication. There's many more, okay? So the weak ties, there's more people, more local bridges. The strong ties, you have less people. Okay, so again you can see, and the connections are tighter. The neighborhood overlap is greater here, going to be here. Okay, so this again is going in the same direction as Granovetter. And the final example is Twitter. So, okay, so let's say, I pretend you don't know Twitter. It's a microblogging service. Users exchange small messages that are called tweets. The users are little birds. And then each user follows other users. Okay, so you can have a tweet is going here. So this user B is following user A. Okay, this is called a follower of A. So B is a follower of A. But then they have this funny word to do the opposite. You can also have the opposite thing is a followee. Okay. This is this. So A is a followee of B, which means A sends to B, okay? Follower of A, that means receives from A, okay? Okay, so I really don't like these words followee, but that's what the book uses, unfortunately. Okay, so you have followers and followees. Okay, now in Twitter you can follow, but you can also send messages directly to somebody, yeah? You can reply directly to somebody, individual, to say that person. So you say it's weak if you're just a follower, and strong if you're actually sending message, okay? And now we can look at how it's related. So this is a graph for Twitter, okay? So here, the number of followees, okay? This is, for a node, how many followees? That means how many people it sends messages to, okay? Number of followees, and here it's the number of really closer ones. You can see the number of followees can go really, really high. You can be sending, a lot of people are following you, in fact. It means a lot of people follow you, listen to you. But not so many people are sending messages back and forth. Okay? So again, these are the weak ties, and these are the strong ties. Okay? So again, you can see that the weak ties, there are many more of them, okay, like for Facebook. The strong ties, it's very small number. Actually, you can explain it this way. Followee is easy to make it very big because it's no extra work. It's passive. You tweet, if you have 10 million people who follow you, then that's no more work than if you had 5, okay? So that's passive. But messages back and forth is a lot more work because you're sending individual messages. So I'm sure Barack Obama, who has like 50 million followers, he doesn't send 50 million messages individually, okay? I don't think, otherwise he's not a human being. Maybe he's not human, but probably he's not doing that. So this is actually, you can explain it from some social reason, okay? So the strong ties are less numerous, okay? Okay, so this is kind of ideas, this is generalizing, and you can see there's a connection between these two, which is similar to what Granovetter said, Okay? Okay, so that's something we saw last week. That's to finish the last week. The idea is that you're taking something that's binary, 0 and 1, and you're turning it into something like continuous, like a number. Okay. Okay, now let's go more into graphs. Okay, now this is the title of chapter 4, Networks and Their Surrounding Contexts, which is a very bad title because it doesn't say anything. But what's really going on here is you are similar to your friends. So now we have friends in the network, okay? So we saw friends and weak and strong friends. But we want to know why they are friends now. So they are friends, according to sociologists. One of the reasons why, or one of the things you can observe, is that friends are kind of like each other. They resemble each other. So this has a technical word called homophily, which is used in the book, okay? There's also another technical word, which is very weird, called assortative mixing, which means exactly the same thing. I just give it to you because maybe you see it somewhere. But basically the idea is very simple. Two people who are friends, usually they're alike in some way. Maybe they both are karate lovers, or they both like to look at Lord of the Rings movies or something. Or for some reason they just like talking to each other. So there's many ways that friends can be similar. And here's one way you can classify. Immutable. For example, age. Young people tend to be friends with people of the same age. It's rare that a 15-year-old person and a 55-year-old person are good friends. Or it's less common than two 15-year-olds, okay? Or racial or ethnic groups, Also mutable characteristics like jobs, or being students in UCLouvain or something like that. So people who are in the same classroom at the same time, maybe there's more chance they become friends, okay? There's some similarity. And here's an example. So here's a big graph. In this graph, each node is a person, and you see the color, no? And it gives information. You can see there's actually 4 parts in this graph, So there's a link when the nodes are friends. You can see there's kind of 4 separated parts, and the links between them are kind of narrow. So this is friendships between students in secondary schools, high school in some American town. So this comes from a study. And there's 2 divisions here. So race, which means whether they're black or white or blue or green or whatever. Okay, here probably it's black and white since this is America. And also age. In the second year you have the middle school and the high school. collège, lycée, the first 3 years, the next 3 years. So you can see that the friends tend to be in the same race and the same age, but not always, okay? It's kind of a trend, okay? The 4 parts. So you can see how similarity affects things. It's not black and white, to use a phrase. It's like very gradual. So here's another example. This, again, is from a United States study. So this is Chicago, the city of Chicago, in 2 times, maps of Chicago, 1940 and 1960. So these are neighborhoods, okay? So the idea, again, is you look at each neighborhood and you see whether the people, how they're similar. So again, this is a study of race. You know that Americans are obsessed with race, okay? So this is a study on race, and people tend to be in the same neighborhood, they're in the same neighborhood tend to be the same race, okay? So the light yellow, the orange blocks, is where you have less than a quarter of African Americans. So blacks in the US are called African Americans, even if they never set foot in Africa, okay? And the darker nodes are more than 3/4 African Americans, okay? And you can see that it's kind of segregated. There's a lot of blacks living here, and here there's mostly whites. And you see that in 1960 you have more, so the percentage of black citizens moved up, okay? So again, you can see that there's kind of an example. The friends here are the people who live close together, and they tend to be the same, their skin color tends to be similar, okay? Okay, so that's an observation. So you can see that this kind of thing happens a lot. And now we want to understand why it happens. And we also want to predict maybe things. And of course on the internet, there's actually 2 ways that friends can resemble each other. It's internal, external. So one of them is called selection, and the other one is called social influence. So those are the words. This is pure sociology. Selection is people select their friends. I choose who are my friends. Okay, and so it's an internal mechanism. It's my choice. I like this person, and I become friend with that person for some reason. And the other thing is an external mechanism. It's called social influence. It's also called peer pressure. Okay, somehow the external world kind of forces me to become friends with certain people, to get to know them and so on. Okay, so maybe it was not my choice, but I get to know them and I can become friends. Okay, so these are the 2 mechanisms. Now, in this area, we want to understand it. Okay, we want to understand why it's like that. How can you understand this sociological fuzzy thing? It's always the same idea. You bring it in the graph. Okay? So we're going to extend the graph so that the reasons why people are friends are in the graph. And then we could start doing graph theory again. Okay? And try to figure out why people are friends and how things will evolve. So in order to make this more concrete, we want to bring this in the graph. And this is not a social network, this is a new kind of network. It's called affiliation network. And so let me show you how it works. Okay, let me for now skip this slide. This is just saying that you have to follow the network over time. Okay. So we're going to add the similarities to the social network. We're going to define an extended graph, okay? Affiliation networks. And once we have that, we can start doing stuff like measuring how strong it is, okay? We can bring everything. So this is the big network. It's called social affiliation network. This has the friends and the reasons why they're friends. They're all in the graph. And this gives us also more kinds of closure. It's not just friends of friends, but also because of similarities, okay? And we're going to see real-world studies. So let me first bring that information into the graph. So why they are friends. So here's an example of an affiliation network. So this is a network with two kinds of nodes. So this is not a social network, right? It's a different kind of network. And I have the people, as before. I have nodes that are people, but I have also nodes that are activities or interests or something, which are not people. And for example, Anna in this graph is a member of the literacy club and the karate club. Okay, so she likes to read books, but she also likes to chop other people. Daniel does not especially like to read books, but he also likes to chop people. Okay, he's also in the karate club. This is a bipartite graph. So maybe you've seen that in graph theory. So that's a technical term. A bipartite graph is a graph where you can separate the nodes into two kinds of nodes. And the only edges you have are in between the two. So you only have edges from people to activities, but no edges between people and no edges between activities, okay? So it's bipartite, so there's like two parts, and you only have edges between them, okay? So you have the individuals, and then you have the activities, which you can call the foci, the focus. It's the focus is the thing that people are interested in, okay? Like karate club, okay? So this is a bipartite graph. Here's another example. So this one is coming from technology. On the left, you see 7 people. John Doerr, Shirley Tilghman, Arthur Levinson, Al Gore, Steve Jobs, Andrea Young, and Susan Hockfield. Okay? And on the right, you see 5 big companies: Amazon, Google, Apple, Disney, and General Electric. And this is the corporate boards. So every big company has a board of directors. Who gets to go on such a board? Well, it's decided by the shareholders and the former directors. So somehow Apple invited Al Gore, who used to be vice president of the United States, to be on their board, okay? So this is in 2009. So you can see, for example, Steve Jobs, okay? Maybe you heard of this guy. He's on the board of Apple, but he's also on the board of Disney. You know, the one with the mouse. So that's kind of funny. So this is an example of an affiliation network or graph, you see? The two sets. And you can deduce things from it. So why is Steve Jobs on Disney? Because the guy makes computers, basically. What does he have to do with Disney? Well, there's this other company that you might have heard of called Pixar, okay? And Steve Jobs was one of the people involved in Pixar, and then Pixar was bought by Disney, etc., etc. So he moved to the media industry. So from this graph, you can actually deduce things, okay? So this tells me things. So that's an affiliation network, okay? Here's another one. This is a much more humble one. This is a primary school, which is like, I don't know, 1st grade or 2nd grade. And these are the children in the primary school, in the class. So you have boys and girls in the class, okay? So the boys are these white nodes, and the darker colored ones are girls. And if the children are friends, there's a link. Okay, so now we can check. So you can see, you can have boys are friends with boys, but boys are friends with girls. Girls can be friends with girls or boys. Okay. So the question is, does that make any difference? Is there more likelihood that a boy will be a friend of a boy or a girl? How can you tell? Because there's both kinds here. Well, here's just an example. We can do actually a statistical test. You can do statistics. If it would be random, if the friends would be random, then we could compute what it should be and then compare and then do some kind of a statistical test. You have seen statistics, and in fact, what we're going to do, you can do something like students' t-test, which you may have heard of. Okay? So the question, is there homophily in this network? Which means, is it true that it's more likely that boys are friends with boys and girls are friends with girls? Is it more likely? Okay? So assume that you have a fraction p are boys and q are girls, so p plus q is equal to 1. And if there would be no homophily, then the edges would be completely random, and you would have p squared boy edges, q squared girl edges, and 2 times p times q boy-girl edges. Okay? So we look at the boy-girl edges. If they are significantly less than 2 times p times q, then we can be sure there is homophily. So in this example, p is 2/3 and q is 1/3. 2 times pq is actually 8 over 18. So this is the fraction of boy-girl friends there would be if there would be no homophily. But the actual fraction is 5/18. It's less. Seems to be different, huh? How can you tell whether it's significant? Well, you have to do statistical tests for this. So one of the things in studying social networks is statistical tests. So I'm not doing a course on statistics, so I assume that you remember very well all what you learn on statistics. So we do a t-test. So this sample mean is actually within the 95% confidence interval. So maybe not, okay? See, so there's 95% confidence interval. If you remember, there's the 95% chance that it would be in there. That means if you really want to be sure it's different, it has to be outside, okay? And the question, so the null hypothesis, are the means of the populations equal? So statistical test is very important for homophily, okay? Okay, so that's basically affiliation networks. You see how it works, huh? Now we're going to combine the two. We have social networks, like we saw last week, and we have affiliation networks, these bipartite ones. We're going to like merge them. Okay? And you can see that both social networks and affiliation networks are going to be changing over time. So we're going to study how it changes. Okay? So new friendship links can be formed. New connections with foci can be formed. So I can join the karate club because my friend George says, you should join the karate club. So I join the karate club, okay? And co-evolution. Two people who have shared focus may become friends, but they have influence on each other, okay? So that's why we combine the two. So we have this bigger network, which has not only people, but also these focus nodes, okay? So we have two kinds of nodes, people and foci, and two kinds of edges, person focus edges, okay? But no focus edges, huh? Because it's bipartite, huh? And then we'll see how it evolves over time. So here we have these closures. So remember triadic closure? It's a very basic thing, huh? Friends of friends become friends. So here's an example. This is my primary school example from 10 minutes ago. But it's actually a social affiliation network in disguise. Because I colored the nodes, remember? They were either light or dark. But that means there's actually two foci. There's boy focus and girl focus. And each node has a connection to either boy or girl, okay? So it's actually already social affiliation network, okay? But I'm going to give you more examples of this network. But first of all, I want to show you how these networks can evolve. So this is the different kind of possibilities that you can have. The top one is what we saw last week, triadic closure. So Bill is friends with Anna, Carl is friends with Anna, so Bill and Carl, maybe they become friends, okay? Because they have a common friend, Anna. So that's the same as what I called strong triadic closure last week. But now we have more kinds of closure. In the second one, Bill and Carl are not friends, and they have no common friends. No. But they're both members of the airplane club, okay? So, and they go to the meetings of the airplane club, maybe they fly model airplanes, whatever, and they become friends because they have this common focus. This is called focal closure. Okay, so Bill and Carl become friends. If you didn't know this, it would be kind of weird. Bill and Carl, who don't know each other, all of a sudden they become friends. Why? Well, if we didn't have this node, we would have no understanding of it. You see that? So adding this node to the graph helps us understand why people are friends. And then we have a third one. This is called membership closure. This is when people add new focuses, okay? So Anna is in the chess club, okay? And Bill is a friend with Anna, so Anna says, hey, come to the chess club, we'll play chess, okay? Bill says, yeah, okay, well, but only if you let me win, okay, or something. But Bill joins the chess club, he likes it. And so Bill has a new focus. Ta-da! So this is called membership closure. So if we didn't have this node, then nothing would happen, okay? If we only look at the social network without this node, nothing changes. But something does change behind the scenes. You see that? Behind the scenes, Bill has an extra activity, okay? So by adding foci to the network, we have brought one of the sources of social network evolution inside the network. And then we can reason about it, okay? So a reason why people become friends. So here's an example of a graph, a social affiliation graph. Remember a long time ago, so I have this kind of obsession with the karate club, okay? So there's this karate club here. And there's also another one called literacy volunteers. This is people who read books to old ladies or something. They help or they teach to little children how to read. So that's also an activity. Then you have a bunch of people here, carefully chosen so that the first letter of the name is going from A to G. Okay? So this you can actually see how it could evolve. So Esther, for example, maybe would join the karate club, okay? Okay, or Bob and Daniel are not friends, but they might become friends, and there's multiple reasons, because they are both in the karate club, but also because they're both friends with Anna, okay? That even increases the reason, okay? And so you could actually use this to predict the future and how the network is going to evolve. Okay, so social affiliation networks are very, very interesting things that let you really understand a lot. Okay. Okay. There's also some empirical studies. So in this course, there's a lot of studies of real internet applications and so on. So we're going to show that too. For example, how much more likely is an edge to form between people if they have more friends in common? You might think if there's one friend in common, they can become friends. But if they have two friends in common, it's more likely. Or three friends in common, it's even more likely. So you want to kind of see what is the likelihood in function of the number of friends in common. So how do you do that? Well, you take two snapshots of the network at different times, and for each number k, you identify all the pairs who have exactly k friends, okay? In the first snapshot, exactly k, but they're not friends. That's just a graph computation. And in the second snapshot, you can check to see whether they become friends or not. And T of k will be the fraction that have become friends. So all the people that had K friends in the first snapshot, but they were not friends, but they are friends in the second snapshot, the fraction is T of K, this function. And you can graph it. You can study this for real networks, okay? And there's lots of data sets for this. And there's one study done by two researchers called Kosinitz and Watts. They looked at email communication among 22,000 university students at a large American university over a one-year period. So that could have been here, huh? They define friends and snapshots. They say a person is a friend if they communicated within 60 days before, okay? And they do one snapshot every day. So they're looking day by day, and then they're seeing whether people are becoming friends. So here you go. Here's the result. And this is actually showing triadic closure. So here is the number of common friends. Okay, 1, 2, 3. It looks like it's fractional, but in fact only the integers are important here. And here's the probability that they become friends. You see that if they have more common friends, then there's a higher probability they become friends. Okay? This is giving evidence, real live evidence for triadic closure. Now, the probability starts at 0 and increases kind of linearly up to 8 friends, and then it goes even more. I mean, if you have more than 10 friends, then it's very hard not to see that person all the time, okay? And you have probably a lot in common with that person, so there's even more chance of becoming friends, okay? And this is what they see in the email. Okay? Notice there's a funny thing here. There's like a hook here. From 0 to 1 friend, there's almost no difference. That's kind of weird. 1 friend is not enough, actually. But once you have 2 friends, then it increases more. This is called the increasing effect. Okay? So it actually really, 1 friend is almost the same as 0. It's not enough to be friends with, to have 1 friend in common somehow. It's what it seems now, what we notice in practice. But if you have 2 friends in common, it's much more. So it's like it's really only starting at 1, okay? 0 and 1 is like the same. This is almost horizontal. Why is that? I'm not so sure. You have to ask sociologists, huh? It's not enough to have 1 friend in common somehow. But if you have 2 in common, that somehow increases much more the chance. Okay. So that's triadic closure. Now, you can also look at focal closure and membership closure. Remember, there's 3 kinds of closure, huh? But first, we talk about triadic. So this is friends of friends. We can make a theoretical model now. So it's really interesting to try to explain why. So let's make a simple model. Okay? Suppose that each common friend gives an additional independent probability of forming a link. That means each time you add a friend, you have extra probability P. That means 2 friends are not the same. They're independently increasing the chance. Okay? So, 2 people with K common friends, they fail to link, so that means there's 0 links with probability 1 minus P to the K. So we're assuming independence. That means we can multiply the probabilities, huh? So each one says probability 1 minus P, they don't befriend, and since there's K, it's 1 minus P to the K. So why am I doing it like that? Because I want to know the probability for at least 1 link. So at least 1 is the opposite of 0. 0 or greater than 0. So that's why I'm doing it this way. So the probability that at least 1 link forms is 1 minus this, 1 minus 1 minus p to the k. So you can plot this, and you can actually approximate it. For very small p, this is just k times p. Okay? Each p gives you an extra thing. So if you look at the graph now, here, these two dotted lines are the theoretical ones. This is for k, this is for k minus 1. Actually, the k model is not as good as the k minus 1. So you assume it actually only starts at 1. So you assume that 1 and 0 friends is like the same, and that it only starts, the p only starts working starting when you go from 1 to 2. The very first friend has no effect, for some reason. You have to talk to psychologists for that, huh? But once you have 2, then the p's, and you can see there's a straight line going up, huh? You can see this is kind of following the straight line. It's not exactly following it, it's actually going a little bit higher. And starting at 8, 9, it goes even higher. So the model doesn't work anymore. You have even more effect than p, okay? So you can see the model gives you kind of a partial explanation. You see that? So we have we observe something, we make a theoretical model, and then we compare the observation with the model, and you can see where it works and where it doesn't work. Huh? Okay, let's now look at the second kind of closure. This one is focal closure. This is focal closure is if the two are members of karate club, then they will become friends. So how many activities or foci do they have in common? Here it's very simple. Two students share a focus if they take a class together. So you guys are sharing one focus right now. If you have another class, it depends then, of course, on which options you're taking, which majors you're taking. You might have other classes in common, okay? So you can say the number of common foci here, so how many classes in common, and here the probability of becoming friends. Again, the same as previous. You can see this is a totally different kind of graph, huh? So it goes up from 0 to 1. So if you take one class in common, you have some effect. Two classes also, but a little bit less. 3 also, maybe a little bit more. And then it kind of flattens off. So you can see focal closure is not so strong as triadic closure, huh? Somehow. And these numbers are smaller, 0, 0, 0, 1. Huh? So there's some evidence. There's less. It's less strong. Okay? Diminishing returns. If you have one class, you have good effect. But after that, it's weaker. So because you have 2, 3, 4 classes, it doesn't change. So it's like in the mind of the student, sitting in one class is the same as sitting in the other class. Maybe you see them more often or something, but the effect is not as strong as actually having common human friends, okay, who are much different maybe than classes. Okay, so this kind of flattens off. So focal closure does have an effect, you see, but it's not as strong as you might think. But this is only classes. You could also think about extracurricular. Huh? Do they go to the same restaurants? Do they like the same beer? Do they like the same films? Da da da. Here it's only classes. Huh? Okay. So there's a third closure also. This one is called, remember, it's membership closure. It's whether you become joint activity. Okay, so this is not anymore for the university. This is for live journal, which is like Facebook before Facebook, and Facebook killed these guys, okay? But you still have statistics on these guys. So before Facebook became the big gorilla in the neighborhood, there were many social networks. LiveJournal was one of them. Here you have LiveJournal has communities, groups of people who are talking about the same topic. might be everyone who's interested in Harry Potter joins the Harry Potter community, you know? Something like that, or mangas or something. Huh? So the probability of joining a community, okay? So as function of the number of friends who are already members. So if I know a lot of people who are part of a Neon Genesis Evangelion community, and I have 10 friends, probably I will join also that community, even though I have no idea what it's all about. Okay? So you can see here the probability of joining a community depending on how many friends who are already members. If all my friends love Lord of the Rings, maybe I start liking Lord of the Rings. Okay? So you can see again, it increases a lot here. Actually, this is a strong evidence, huh? It goes up a lot, huh? I mean, it flattens off a little bit, but at high number, up to 20 or so, it's still increasing, huh? So the effect is quite strong. But the marginal effect, so the effect between two numbers, the marginal effect, it stays pretty strong for a long time. So much stronger than focal closure, huh? So joining groups, joining communities is really affected by your friends doing it. And also the funny effect at the beginning is also there. 1 is not enough. From 0 to 1 it's very small. It only really starts growing when you go from 1 to 2. So this is the increase, what's called the increasing effect. The 2 is worth more than twice 1, okay? So one friend being Lord of the Rings, people say, nah, it's bogus. But if I have 2 friends who like Lord of the Rings, then I say, maybe there's something there, okay? So somehow the 2 friends is much stronger than 1. So why is that? I don't know. I mean, but you can observe it. See, you can observe the effect. So you can see the 3 kinds of closure are all active, and you can see it. Huh? Here is another study on membership closure. This is for Wikipedia. Okay? Now, this is for the Wikipedia editors. Okay? I don't know if you've ever edited a Wikipedia article. Any editors of Wikipedia here? Yes! Oh, great! Okay, excellent. Okay. So, the probability of editing an article, so the one who's actually writing the article, depending on how many friends who read that. So the group, the editors of Wikipedia, are like, they know each other a bit, and sometimes they're friends, okay? And you can see that the more friends you have who are editing, for example, the article on Donald J. Trump, the more that you have the chance of doing it too, okay? And again, there's this funny bump between 1 and 2. We see it many times. So there's something there, huh? 1 friend editing Trump is not enough, but if I have 2 friends, then I will have much more chance, okay? It also keeps growing. And it doesn't flatten off so much, so that it continues as strong evidence. And there's also this funny increasing effect that 1 is not enough. So this is interesting, right? It lets you observe. If you want to influence, it's not enough to have 1 friend, you have to have more than 1, okay? For joining something, okay? So you can see that the 3 kinds of closure are really active, huh? Triadic closure, focal closure, membership closure. So you can use them to really understand how it evolves. Okay, now there's one more thing I want to understand in these networks is selection and social influence. So the peer pressure or the internal choice. Why do I become a friend? Is it because I choose, or is it because somehow I'm forced by my surroundings to do it? I mean, I choose because of my surroundings. You can also compare those. Okay, so we're going to compare those too. Okay, but let me make now a small break, and then we'll compare, and we'll see how you can actually see peer pressure in action. Okay. Okay, so let's make a small break. On va faire une petite pause. Very good. So now I want to try to understand something else, actually something which is kind of subtle. Selection and social influence. Actually, it's kind of hard to understand how it works. Selection is internal, remember? I choose to become friend with this guy, for example, because it's my choice, and they also choose, okay? But it might be social influence. I'm in a circle of friends, and there's one person there that is not my friend, and I become friends with them because I'm in the same friends circle, okay? So you have the external influence and the internal. So now I want to see how can we compare them. So this is a very delicate kind of distinction, okay? How do you know whether it's internal or external? It's internal is what happens in somebody's mind, but also the social influence is also somehow in the person's mind, because it's the person who says, I'm now friends with somebody, for example, but how did they become friends or why? So let's see whether we can compare the two. So I'm going to give you now an example of a very interesting and a very subtle study that was done to compare those two. And it was also using Wikipedia. We want to separate two parts of network evolution. One where you have selection and one where you have social influence, and then we can compare them. Okay, so this is actually not so easy to do. This study is actually a very interesting and very intelligent way. So it's good to think, how does it actually compare the two? This one is on Wikipedia again. So let me recall now also a little bit what is Wikipedia. It's a collaborative encyclopedia. It's written by editors. And the editors, anyone can become an editor. You can join editor, but then you're in a community of editors. So the editors have protocols how they work together. We're going to study the behavior of these Wikipedia editors, okay, in terms of selection and social influence. First, let's define the network. Two editors are linked. They're considered to be like friends if they have communicated on their talk page. So each editor has a talk page where you can discuss. For example, two editors are editing an article on quantum mechanics. They're both physicists, and they are discussing what's the best way to explain something, okay? So they have talk pages. And if they are talking together on this talk page, they are linked, okay? But if they don't talk on the talk page, they're not linked, okay? And the behavior of the editor, let's say, is the set of pages. So each editor has a set of articles that they edit. So for example, maybe a physicist could edit lots of articles on quantum theory or something, but maybe also articles on Immanuel Kant's philosophy, if they like that. So every editor has a set of articles. We can define the similarity between editors through the articles they edit. Okay? So the number of articles edited by both A and B, two editors, divided by the number of articles edited by at least one. Actually, you can see this definition is actually very similar to neighborhood overlap, where the neighbors are the articles that they edit. So if A and B are editing exactly the same set of articles, the similarity is 1. If they edit 0 articles in common, the similarity is 0. And in general, it would be some number between 0 and 1. This is showing how similar they are, okay? So this similarity is how the editors are alike. This similarity is going to change over time, and what we are going to do is see how it corresponds to selection and social influence. So here is the graph that this study came up with. So this is a very interesting graph. So let me explain first how the graph is made. On the horizontal axis, you have the 0 is when two editors first meet. That means the first time one of the editors is on the top page of the other. That you place 0. Anything after that, any other edit after that goes on the positive side, and edits before that go on the negative side. Notice, before they didn't know each other, okay? Because we're collecting all the data and analyzing it later, we actually know what the editors did before they got to know each other, okay? And in terms of this, so this is like normalization, huh? We look at all pairs of editors, we compute the similarity, and we compute the average similarity of all the pairs of editors, but relative to the first instant when they met. Okay? And this graph is shaped like an S. It's very funny. Okay? Now, on the left, you can see the similarity is always increasing. Okay? But on the left, they didn't know each other. They didn't know each other, so all increase in similarity is because of their own decision in their head. Okay? It's due to selection. And after they know each other, they are discussing, so they take the other one into account. So if two physicists are working on quantum theory, maybe they will split the pages. Say, okay, I will talk about quantum electrodynamics, and the other guy will talk about quantum chromodynamics, and then we split like that. But they can only do that when they know each other. Okay? So that's a social influence. The behavior of an editor depends on the other editor, not on their choice. So that's a social influence. All the change in similarity after the contact is due to social influence, and the change in similarity before the contact, because they did not know each other, it could not be social influence, and they didn't know each other. It's due to selection. It's due to their own thinking. Okay? So you can see what happens. The similarity is increasing, increasing, so they're getting more and more similar. Why is that? Well, because we know that at point 0 they're going to finally talk to each other. So I have two physicists who do not know each other. They're working. They're getting more similar. At some point they will meet, okay? That's the point. At some point they will talk to each other. So the similarity is increasing, increasing, higher and higher until they meet, boom. But once they meet, they discuss, and the similarity will not increase so much because they will separate themselves now because of the discussion. You see how it flattens. They will separate the work, maybe, or partition the pages. They will do, okay? The editors will adapt to each other after they meet. That is due to social influence. So you can see here the effect of selection and the effect of social influence. Okay? Of course, this is a very special case. Usually, in general, it's very hard to separate the two. But in this case, you can separate the two. Okay? So you can see that the reason why they meet is because they are becoming more similar. And that's independently. Okay? There's no connection between them, at least not on the Wikipedia. They don't know each other because, I mean, maybe they know of each other, but they never have discussed together. So the knowledge is very weak. But as soon as they know each other, the interaction changes completely. Okay? So that's one way that you can actually distinguish between selection and social influence. Okay. Okay, so that's all analysis of closure. How friends become friends. And we saw real studies. So closure is a real thing. It really exists, okay? Of course, there's still a lot of questions. So what I'm telling you, the research that I'm telling you, is not finished. It's ongoing. So this book is like from 10 years ago, okay? But in those days, the internet was already very big, and many of the conclusions in here are the same, or a little bit more studies have been done. But the internet is a very new thing still. And so all of these results are only the beginning. Okay? So this analysis, what I'm showing you, is just small pieces. It's still early stages, okay? So maybe when we do the project, the course project, we will try to do some kind of a new analysis, who knows? And if some people who are really interested in continuing this could do a master's project or even more. I had one point, a student who did a master's project on analyzing trust in networks, and it actually got published in a workshop on trust analysis, and it was in China. So the guy went to China. It's not bad for a master's project, huh? But what I'm saying is that this is all still in progress, okay? Okay, let me now take the final topic of the day, which is positive and negative relationships. So when you have enemies, not just friends. Previously, all the links are positive. But now let's go even farther and add negative links. Friend versus enemy. The links can now be positive or negative, and we'll study the tension. And this introduces a whole new idea, in fact, the concept of structural balance. There's some kind of a balance between the positive and negative. And also how small local effects can have big global consequences, okay? Okay, so let me talk about positive, negative, and structural balance. We're going to talk now about networks where everybody knows everybody. So this is for simplicity. Huh? In previous networks, we had friends, but also we have nodes that don't know each other. Okay? But now when we have the plus and the minus, we assume that all the nodes know all of each other, all of them. Okay? So this is called a complete graph. Okay? So all of the nodes know each other. There exists an edge joining every pair. So if I have 5 nodes, for example, I have edges joining all pairs. Okay? Like that, for example. You have 5 nodes and edges joining every pair. And on those edges, you can have a plus or a minus. Okay? Plus, plus, minus, minus, whatever. I'm just doing random here. They could be enemies or friends, these nodes. Now the question is, what can we say about this? This is called, by the way, a labeled complete graph. So a complete graph, it's also called a clique. A clique. So clique is a technical term. It means that there's edges between all the nodes. So for now, we're going to talk about complete graphs, or cliques, and we're going to label them with plus and minus. Okay? So there's only plus and minus. There's no indifference. There's no zero. It's either plus, either I'm friend, or I'm enemy. No middle ground. Okay? A small group of people that are mutually aware. This is a small group of people where everybody knows everybody. A classroom, here. A small company where all the employees know each other. A sports team, all the players know each other. A club, a board of directors of a company. Countries, international relations. This is what's modeled here, okay? In this, what I'm going to show you now. And I'm going to introduce a concept called structural balance. And again, we look at triangles. Triangles are very important. Remember, before the break, I talked about closure. Closure is where you have two edges of a triangle and you add the third one. So it's about triangles. Well, now, again, I'm going to talk about triangles. Okay? I'm going to talk about triangles between three nodes. Here, for example, A, B, C. And the triangles can be balanced or unbalanced. So I'm going to introduce some notion whether the triangle is a kind of like a stable, nice one, or whether it's kind of stressful. Okay? And of course, a graph has a lot of triangles. Okay? And we'll see that the real world doesn't like stress or unbalance. It's all going to evolve towards removing the stress. So these triangles can be either stressed or not stressed. So here's the possibilities. So here are the triangle, as a triangle, ABC. So on left I have a situation where I have three friends. A, B, C, plus, plus, plus. That's very nice and that's stable. That's a nice situation. Okay, in the middle, for the second one, I have B and C are friends, but they have a common enemy, A. B hates A's guts, and C also hates A's guts, and mutually. But B and C are friends. This is actually balanced, because there's nothing is pushing this to be changed. B and C are, everybody is agreeing in a sense, B agrees with C, C agrees with B, and they both agree to hate A, and so on. So this is also balanced. Okay? Now on the right side, there's actually two more situations. And these are not so balanced. For example, when everybody is an enemy, and there are all three of them, that's kind of stressful. So many enemies, okay? B is an enemy of A and C. C is also enemy of A and B. No friends in sight. But the final one is an interesting one. A is friend with B, and A is friend with C, but B and C are enemies. So when A organizes a party and invites B and C, which are A's friends, maybe they start fighting each other. Who knows? So this is a stressed situation. A is friends with two people who are enemies. That's kind of stressful for A. It's kind of stressful for A. It's stressful for B also. B is friend with A and enemy with C. But because A likes C, B will find C in the same room. Okay? Very dangerous. Okay? So these are the four configurations. So we will say a triangle is balanced if it's in the left situation. It's a very stable, natural situation here in the two on the left side. And we'll say it's unbalanced if it's one of the two right situations. Okay? So we have balanced triangles or unbalanced triangles. Okay? Okay, so now we're going to look at that and see what we can read, what we can understand about that. Okay? There's an empty part here because this is something that I will draw, okay? And when I drew this last year, it was on Teams, but I will draw it on the board today. So a labeled complete graph is balanced if for each triangle, the links are plus, 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 or plus, minus, minus. Those are the two balanced ones. Huh? Each triangle is balanced. So if I have a graph here, let me make a graph, some kind of a graph. For example, A, B, C, D, E. Okay, let's say I have plus, plus, minus. So that's balanced. That's actually not good. Plus, minus, like that. I have here another minus, here a plus. Okay, So this one, this is a plus minus minus, this one is plus minus minus, here you have 3 pluses. This is a balanced graph, okay? Right, huh? I could also change it a little bit and still be balanced, huh? I could do like this, and it would still be a balanced graph, huh? If I now do something a little bit different, for example, okay, now I have an unbalanced graph. Now I have stress, because these two are enemies, but they're both friends with C. So A and B are enemies. But C and E are enemies also, and they're both friends with B. So this is a kind of a stressful, unbalanced graph. Okay, so this is kind of how it looks. But the definition that I give you here is a local definition. It means it's a definition about all the triangles. What I would really like is a global definition. I want to see the whole thing. Okay, in fact, you could make a global definition of balance too. And this gives a theorem, which is called the balance theorem. So let me explain what it means. So this was actually proved by a famous graph theoretician called Frank Harari in 1953. So graph theory is a fairly recent area. We have a labeled complete graph. It's balanced. Then either all pairs of nodes are friends, or the nodes can be divided into 2 groups, X and Y, such that the nodes inside a group are friends, and the nodes between the groups are enemies. Okay? So basically, if the graph is balanced, either everybody is a friend, or you have 2 groups of friends who are enemies between. So somehow you could organize the whole graph like that. That's interesting, huh? This is a global property, because it's a property of the whole graph. It's not just a property of a triangles, huh? So there's actually 2 groups. You can split the graph into 2 groups, always 2. Yeah, either 1, if there's no enemies at all, or 2. But never 3 or 4 or anything, only 2. Okay? So that's interesting, huh? Okay, for example here, if you look here, so this graph is balanced, huh? Okay, it's balanced. Well, actually, you can split it. You can say, this is a group of friends. Here also I have a group of friends, and those 2 are enemies between them. You see that? And it's always true for a balanced graph. You can always split it into 2. But it's not true for unbalanced graphs, huh? Only for balanced graphs. Okay, now I will show you the proof of this. This is very interesting proof. Okay? And remember the direction we're going, huh? If it's balanced, then you can split it. Of course, you can also go the other direction, huh? This graph, a graph like this, is always balanced, but that's easy to show, huh? You either have plus, 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 or you have plus, minus, and you only have that. So, but it's the hard direction we're going to do, We're going to assume it's balanced. That means all the triangles are balanced, and we're going to prove it has that structure. So now I will give you the proof of that. Okay? And you have to understand that proof. It's important to be able to reason on graphs. Okay? So we're going to do the proof. Okay, so we suppose that we have a labeled complete graph, and it's balanced. We have to show that it has the global property of the theorem. That means the 2 groups of enemies. Two groups of friends who were enemies. Huh? That is the direction. In previous years, I always find people who try to prove the other direction. Don't confuse the directions, okay? We do it in this direction, which is the hard direction. Okay, so let's do the proof now. Okay, so there's two possibilities. If there's no negative links at all, then everybody is friends and we're done. Okay, it's over. So we will assume there's at least one negative link. Okay, there's at least one negative link. Fine. Okay, now, how do we prove it? Well, usually when you want to prove something, you need to add some structure. Because now we're like in front of this unknown thing. How do we prove it? Well, we add something. So we pick a node. Pick a node A. Any node A. And we will study the graph from the viewpoint of A. Okay? Okay. We're going to define two sets of nodes, X and Y. X will be A plus all the friends of A, and Y will be all the enemies of A. So all the nodes in the graph, we put some of the nodes here. So all these nodes are friends of A. Okay? B, C, whatever. There might be more, huh? And then here we take all the nodes that are enemies of A. So this is a minus. There might be a second one, who knows? It's like that, but there could be more. Huh? So X is A plus all of its friends, and Y is all of the enemies of A. Okay. Now we have two sets, X and Y. And now actually it's very easy, because these two sets are the two sets. They are the mutual friends who are enemies. But we have to prove that. So the question, do X and Y satisfy the theorem? So we've constructed X and Y. So we have to show three properties now. We have to show that all the nodes in X are friends. And make it like that. That all the nodes in X are friends. We have to show that all the nodes in Y are friends. And we have to show that nodes between X and Y are enemies. Okay? Every node in X is an enemy of every node in Y. We have to show those three things. Okay? And no more, no less. Okay. So here is the proof, but it's written in white font. So it's kind of unreadable. But I can see white font. Okay? When you become a professor, you can see white font. It's one of the privileges of being a professor. So I know the proof. So let's take a look at the proof. Remember that the graph is balanced. So what does it mean, balanced? Balanced means that all the triangles are either this, or... So what's the second one? The second one is you might have two friends with mutual enemies. Then you have only this, those two triangles. Okay? Good. Let's take two nodes in X, B and C. They are both friends of A. We know that. That's the definition. Okay? So what does that tell us about this link? We have plus, plus. We have plus, plus. There's only one possibility for the third link, which is a plus. Here we only have one plus, So we don't have this situation. So this one must be a plus. See it, huh? Okay, let's take two nodes in Y. They are both enemies of A. That's the definition, huh? So what about between them? Well, we have a triangle with two minuses. Minus, minus. The only other possibility is a plus for the third edge. So it has to be a plus. And the final thing, we have a node in X and a node in Y. We have a plus and a minus. So what is this link? We have one plus and one minus. Well, here we have three pluses, so it can't be this. Here we have a plus and a minus. So the other one must be a minus. Okay? And now we have shown it, because these are arbitrary nodes, huh? B, C, D, and E. We have shown that all the nodes here are friends, all the nodes here are friends, and in between them there are enemies. Q, E, D. Okay? Of course, you can apply this. Actually, politicians know this theorem very well. Here is an example, kind of complicated. I won't go through everything. Okay? This is the separation of Bangladesh and Pakistan in 1972. Of course, you remember it very well. I won't go over the full details, but in those days, there was a country called the USSR. Do you remember the USSR? Yeah. Yes, I remember it well. It was enemy of China. China was enemy of India. India was enemy of Pakistan. The United States wanted to improve relations with China, so it supported the enemies of China's enemies. Okay? So it supported Pakistan. Okay? North Vietnam became friendly toward India. Pakistan severed relations with Eastern Bloc countries who are friends of USSR that recognized Bangladesh, and China vetoed the acceptance of Bangladesh. Okay, if you make a graph, you can see, you can explain all of this in terms of structural balance. Okay? Okay, here's another example. So this one also is very well known for historians. Okay? So it's a trivial example. I'm sure you all know it very, very well. This is the shifting alliances in Europe between the 1870s and up until the start of World War I. So we have 6 countries here: Great Britain, France, Russia, Italy, Germany, and Austria-Hungary. Of course, you remember very well the Austria-Hungarian Empire. I'm not going to explain that. In 1872, this is there was what's called the Three Emperors League, okay, which was a league between Austria-Hungary, Germany, and Russia. 3 countries where they had emperors in those days, okay. Then we had the Triple Alliance, or the Triple Alliance, I'm not sure how to pronounce it. That's B, where Italy joined, okay. So the dark lines are friends, huh? Okay, C, we now have the German-Russian lapse. This is funny. There was a treaty between Germany and Russia of friendship. And when the treaty ended, nobody remembered that they had to sign another treaty. They somehow forgot, so there was no more friendship between Germany and Russia, and Austria-Hungary then followed suit. Okay, and indeed, we had the Franco-Russian alliance. Okay, in E, we had a very famous situation, which was called the Entente Cordiale, between Russia, France, and Great Britain, and on one side, and the other 3 on the other side. And now, in 1907, we have the British-Russian alliance. You can see it's kind of a closure example. Now we have 2 groups of enemies looking at each other. So this is a perfect situation to start a war, okay? And the war started from that situation, okay? So this you can kind of understand through structure balance. Yes, question?
Donc, quand il y a des relations binaires dans un graphe, le résultat est déterminé à l'avance.
Sorry, take off your mask.
Je disais que quand il y a des relations binaires entre les pays, enfin le résultat du graphe est assez, on peut le déterminer à l'avance parce qu'il sera optimisé.
Oui, on peut le déterminer à l'avance. So yeah, so you could kind of predict what's going to happen because stressful triangles are going to try to disappear, okay? And so a triangle with stress will disappear. Okay, there's a third example I want to present, which is user communities. So this is not for the web. You can have like and dislike, trust and dislike. But now it's more complicated because the trust and the distrust, is it commutative? If A distrusts B, does B distrust A? Usually it is. Is it transitive? If A trusts B and B trusts C, will A trust C? Sometimes. okay? But distrust is not necessarily transitive. A distrusts B, B distrusts C, will A trust C? If it's like being an enemy, then maybe yes. But sometimes distrust is where you believe the other guy is incompetent, like opinions on movies. I don't trust the opinion of this guy on the movie Lord of the Rings because I think this guy is an imbecile, okay? And so it's probably not transitive. So in that case, the A would even distrust C, okay? So if you look at, there's a site called E-Opinions with trust and distrusts. So this one is sort of like political alignment, okay? A trusts C is plausible, okay? It's transitive. We're rating product. Trust, distrust models expertise. So A distrusts C is plausible. If A thinks B is not an expert, and B thinks C is not an expert, there's no reason that A will think C is an expert. Okay, so the point is that be careful. So this is actually to show that structural balance is only one way. You have to be a little bit careful. And to finish then, I will introduce an alternative to structural balance, which in politics is even maybe more useful than regular structural balance. This is called weak structural balance. Okay, so remember, structural balance is where you allow these two triangles, okay, but no others. Okay, well, we can actually change a little bit the definition. Notice that we're very free to make definitions, okay? We can make an alternative by changing what we think is balance, okay? So remember, we have these two other triangles, plus, so we have plus, plus, minus, and minus, 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 okay? And those are would both be unbalanced. But maybe we can have a weaker version of it. Okay, so we can say plus, plus, minus actually has a good chance of changing, of evolving. If I have two friends who are mutual enemies and they come into a room together, maybe A, so A is the one with two mutual friends, A is going to try to reconcile them. Say, come on, you guys, let's drink a beer and all be happy, you know. And B and C will say, okay, I mean, I don't care whether we vote for Trump, I still think you're a human being, okay? So they become friends again. So this triangle, we can say, it's actually not very stable, it could be balanced, okay? So that means the minus, minus, minus triangles, though, these are kind of pretty stable. They won't change. Everybody's enemies, and there's no force of reconciliation, okay? In this one, A is like a force of reconciliation, whereas in the minus, 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 there's nothing there that will push the triangle to change, okay? So that means this one is actually kind of a stable one too. That means we can actually have a weaker version of structural balance. We can call it weakly balanced. We keep the plus, 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 and the minus, minus, plus, but we add the third one. We add minus, 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 because this one is kind of a stable one, okay? And so this situation will kind of change. We only disallow the one is this one. We disallow because this one is not so stable as the others because there's a force of reconciliation. The A node will try to make this minus turn to a plus. So this one it's not really as stable as the other. So we can define a version of balance that's a little bit weaker than this one by adding the minus, minus, minus. Okay? So we allow minus, 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 because it's kind of stable. It can happen that everyone is enemies, okay? But we disallow plus, plus, minus because they tend to disappear. Question?
Oui. En fait, au lieu de décrire une relation binaire avec des plus et des moins, pourquoi on n'utiliserait pas un réel ou un complexe pour
Wait, so the question, why do you use plus and minus and not your real number? And the answer is yes, you can use real number. But let me first talk about plus minus. There's a whole books have been written about structural balance theory, and sometimes they use real numbers. But I don't want to spend the whole course on this, so I'm only going to give you one example. So the answer is that there's a lot of variations of this, and including real numbers. But let's just look at this second version. Weakly balanced. And then there's a theorem called the weak structural balance theorem. This one is actually really neat and interesting. So if the labeled complete graph is weakly balanced, you can divide the nodes into groups such that inside the group you have only friends, and the groups are always enemies in between. So this is kind of a very interesting variation of the regular balance theorem. So remember here with the balance theorem, we show that there's actually two groups in the theorem. Whereas if you have weakly balanced, you can show that you can have more than two. You have n. And it could be any value of n. It depends on the graph. So the situation is like this. So here's an example with 5, but it could be 4, 3, any number. It depends on the graph. Okay? And let's prove this. So we're going to prove this. I'm going to finish by proving this. This is a really interesting proof because how do you prove n? We want to prove there's a division in n groups, but we don't know n. So how do you prove that? And the way to prove that is to use recursion. So the proof is going to be a recursive proof. It's a really interesting proof, and it's not so complicated. Again, it starts the same way as the previous one. Okay, we pick a node A. Pick a node A. And all of its friends. This time we're only looking at A and its friends. So these are friends of A. Okay. And all the other nodes are in Y. They are not friends of A. They are not friends of A. Okay. So this is a group X. But now we have 3 triangles instead of 2. So we can't really use the same proof as before. So what are we going to do? Well, let's just look at the group X now. Let's just say that we want to show that all the nodes in X are mutual friends and that they're enemies between all the rest. But we don't know anything about what happens in Y. So we don't know that the Y's are friends. We don't know. Okay? But we do know, we will know that X nodes are enemies with everybody else. So let's just focus on X. All nodes in X are mutual friends, and all nodes in X are enemies with all other nodes. That's something that we can try to show. Okay? So let's try to show it. Okay, so here, for example, is a link between B and C. So what is the value of that link? Plus or minus? Now we have 3 possible triangles, but we have 2 pluses. But the new one is minus, 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 so we don't need to look at it. So this is the only triangle that works, so this has to be a plus. Okay, what about between B and D? We have a plus and a minus. A plus and a minus. So it's not this or this one, it has to be this one. A plus and a minus. So the third one has to be a minus. Okay, good. What about this one? What can we say between D and E? You tell me. Does somebody see? What can we say between D and E? Given this. We have a weakly balanced graph. The D and E are both enemies of A. What about D and E? Yes?
They can be friends.
Sorry?
They can be friends.
It can be friends?
Yeah.
Are you sure? Are they always friends?
No.
It can also be enemies, right? So D and E could either be both. You could have either minus minus plus or minus minus minus. So actually we don't know anything. It could either be plus or minus. Both of them are possible. So actually we don't know anything about DE. Okay. But we do know, what we do know is that all the nodes in X are friends. And all the nodes in X are enemies with Y. What we do not know is what happens inside of Y. Okay? Okay, so we can remove X from the graph. This one is actually the first group in our n groups. It's the first group in our n groups. So we remove it from the graph. Remove it. We are left with Y. This is our new graph, Y. And we know that X is enemies with all of them. Now look at this new graph. Y is strictly smaller than the original graph because the node A is moved out. So even if X is almost empty, there's always one node less. Okay, let's look at Y. If Y is empty, we're done. If Y is not empty, we do exactly the same as we did before, but with Y. So we pick a node inside of Y, we call it A, and we keep going like that. And then we will split Y into another group. Let's call it X prime and Y prime. And this one, these are all enemies, and these are all pluses. And then we continue with Y prime, and we keep going like that. You see that we do recursion. And eventually we'll end up with an empty set because we're always going to be removing at least one node, so it's always strictly less. And so ultimately we arrive to partition the graph into n nodes, and that's it. And that's the proof. It's interesting, right? You see how the recursion is working, huh? And this is a summary of the whole thing. So let me summarize everything now. So these are the four kinds of triangles. So there's four situations. Either I have only this one, everybody's friends. That's trivial, I have one group. Or I have these two. That's what I call structural balance. Then I have two groups. Or I have these three. Then it's what I call weak balance, structural balance. Then I have n groups. Or I can have all four, and then I don't know anything, okay? It's a mess, okay? Therefore, if I have all four, then the thing will evolve, of course, but the top one will tend to go away. And eventually, maybe I go back to a weak structural balance. So you see, with this structural balance, you can look at groups as groups of enemies and friends, okay? Okay, so let me summarize it. Okay, so we made plus and minus, okay? And we had two forms, structural and weak structural. And it's kind of an equilibrium, Groups are always evolving, So in structural balance, you will have two enemy groups. But in weak structural balance, you will have n enemy groups, okay? And there's lots of applications of this. And this is actually the tip of the iceberg. There's actually a lot of theory that goes even farther than this. And politicians, of course, know this very well, even if they know it intuitively. Okay. Also, Tour de France, where you have teams of cyclists. So I didn't go into this kind of examples. But if you have more antagonism allowed, then you can have lots of enemy groups. Okay. And okay, so let me stop there, and that gives you then an idea of how graphs help you understand the social networks. Okay, so I stop here for today.